nanoHUB.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
So, this morning we talked about this quantum transport, and what I'll be talking about now, though again in a way we'll be going back to the semi-classical picture, because much of what I want to illustrate is how this elastic resistor model you can use to understand all kinds of different physical phenomena. And what I'll be talking about is thermoelectricity and heat flow. And for that, again, one could include quantum effects. It's just that basic things you can understand fairly well without bringing in any quantum effects, really. So we can go back to the semi-classical picture. But before I start on that, let me just say a word about just summarizing what we did in the morning. And that was that, as you know, the basic thing I was trying to express is how in semi-classical picture, just as the Boltzmann equation is the central thing. I mean, it's anything you describe is basic. Boltzmann is what captures all the physics. The point is to understand it and try to use it. And the elastic resistor then is a good way to understand a lot of phenomena. The kind of quantum version in my mind is this NEGF. So in a way, what Boltzmann did, and this was his crowning achievement of this 19th century in a way, is he took Newton's law and he put scattering and all that into it and turned it into Boltzmann equation. You see, Newton's law, which describes mechanics, reversible processes. Into that he included these irreversible scattering processes, and thereby came up with this equation. And as I said, what he did was so subtle that in his time it was very controversial, and even now you see people writing phys rev letters, papers in phys rev letters about what exactly he did and the meaning of it and the implications of it. Okay. But the point is that just as Boltzmann needed to do something with Newton's law to get all that in, once you replace Newton's law with Schrödinger equation, quantum mechanics, you again have to do something similar. This is just as Newton's law wasn't enough, Schrödinger by itself isn't quite enough. You have to do something else. And NEGF is one way I know, which essentially does that in a consistent way that is comparable to Boltzmann in exactly the same way. And those were the equations of the Boltzmann, of the NEGF formalism. And what it includes, of course, that is different from Boltzmann is that it includes interference effects, essentially. And as I said, if you are trying to learn this, then two good examples to go through are first the one-dimensional example that I mentioned, about various scatterers, see how you get resonances out of the quantum. If you want to include dephasing processes into the NEGF, then you can actually turn the quantum calculation into the classical calculation by destroying the interference. So that's usually a nice example to go through. The other example, I say if you are kind of comfortable with the 1D, then I'd say let's try the 2D. And a good 2D problem is this Hall effect problem. Just a 2D conductor, you can first calculate conductance without any magnetic fields, then see what happens in a magnetic field. And one of the interesting things that actually happens in a magnetic field, which I won't go into, is that at high fields, you see that Hall resistance, you'll see show those very sharp plateaus, very nice plateaus. And that was the first example probably where this quantum of conductance played a very important role, in the sense that Hall resistance actually looks like h over q square times an integer. And one way to understand it in the context of what we are talking about is that what happens at high fields is that the electrons that are going in one direction tend to have their wave functions on this side of the sample, while the electrons that are going in the other direction tend to have their wave function on that side of the sample. So as a result, you have almost a very good ballistic conductor, because you see it's very hard to backscatter if that other thing is way out there on the other side, essentially. So something non-trivial happens. That is, usually in a conductor, you expect the density of states to be more or less uniform, spread out all over. But in this high magnetic field regime, actually you have what you call these edge states. And these are things, of course, there have been lots of papers about it and in terms of understanding all this. And as I said, the power of NEGF is how it allows you to calculate a lot of this, even if you don't quite follow what have happened. And so, for example, in the NEGF equations I showed you, there was something I call density of states. There's a matrix there. Just as there's an electron density matrix, there's a density of states. And you could look at its diagonal elements and actually plot out what the density of states is at different points in the sample. So, for example, here I've shown a calculation at high magnetic fields. So what is over there is this grayscale plot. This axis is energy. That axis is the width of the conductor. And if you see a white spot, it means there's a lot of states there, high density of states. So what you're seeing is the spatial distribution of the density of states. How was this calculated? Again, with NEGF, you put in H sigma, etc., and using those equations, you calculate it. And you see those white spots in the middle. Those are what are called Landau levels. Actually, at high energies, at high magnetic fields, you have discrete levels at different energies. But the interesting thing is, if you look, there's these white streaks. I don't know if they come out here well. You do not see this very well. Right near the edges, there are these white streaks, which are basically the edge states. Actually, I see that well on my screen, not as well up there though. But right around the edges, there should be these white things. And the way people think about it is that, well, electrons in a magnetic field, they want to turn as you know, in a magnetic field, they want to go around like this. Why? Because the understanding is that dp dt, as you know, when you do semi-classical dynamics, dp dt is equal to force. So it's like Q V cross B. And if your magnetic field is perpendicular, then it tends to turn you. And this you can show that as a result you want to turn, and if you're in the middle, you will tend to go around in circles, and those are the usual Landau levels, etc. But when you're near the edge, you'll tend to do this. Hit that, do this. This is what people call skipping orbits. And that's how people sort of picture where the edge states came from. Whereas ones that are going this way tend to do this. So all the northbound people stick to one side, southbound people stick to the other side, so makes it a perfect ballistic conductor in a way, you see. And net result is if your Fermi energy happens to be there, the actual, this resistance is given by this without any backscattering almost. Whereas usually with ballistic conductors, they are kind of semi-ballistic in the sense that you get Q square over H times M within a factor of maybe 5% or 10%, because there's always some backscattering. But what made this quantum Hall very special when it was discovered in the early 80s was that the resistance they measured was like quantized to like the 7th place in decimal. It was very accurate. Something you never expect in a solid. Usually to make measurements that accurate, you have to go to vacuum. You see? So that was what was really surprising and unique about it. And I think that was probably the first experiment where this quantum of conductance kind of played an important role. These are fundamental constants which have been known a long time, but this combination was not quite as well recognized in general. Right? So there's one experiment where it actually played an important role. And again, so as I said, if you are trying to learn NEGF and doing, this is a good test problem once you have done the 1D thing, because 2D has more details in it that you have to worry about. Okay. So what I wanted to talk more about then today in this lecture is about the heat flow. That's the second, the topics down here. Right? What we talked about in the morning was what's up there, this thing. And the basic fact, experimental fact is, I guess, let me explain this, is that if you take a piece of semiconductor, then one experiment that is very easy to do, I guess even I have done this, is that if you put down two probes, one hot and one cold, then there's a current that flows, even without any voltage. Right? Or if you don't allow the current to flow, then a voltage would be developed. Right? So this is what the hot point probe experiment. So in this picture, I could say that if this side was hot and this side was cold, then a current would flow in a certain direction. And the thing is, the interesting point is that the direction of that current is different in N-type semiconductors and in P-type semiconductors. Okay? The question is why? And what I claim is that we don't need anything new to understand this. That's all right here. If you just take this, and the way we said it was the Fermi functions in the two contacts are different because you have applied a voltage. We had two different chemical potentials. But supposing we consider the situation when the chemical potential is the same, I have not applied any battery, any voltage across it, just the temperatures are different. Of course, that would make the Fermi functions different, because you see the Fermi function is E minus mu over kT. Usually the reason F1 is different from F2 is because mu1 is different from mu2. But let's say no voltages. All the mu's are the same. But that's fine. The F's are still different. There's a kT1 and a kT2. They're two different things. And that's why you have a current. And what I claim is, that will, just from this point of view, you understand all the basic things of thermoelectricity, the standard stuff. Right? That's what I want to get across. So the picture I had drawn before, you had a density of states here, and you have a mu, and this is mu1, and this is mu2. Yeah, so let me draw this here. So when I draw the Fermi function, the way I want to draw it is both sides have the same mu, but they have different temperatures. So this is the hot side. So I'll draw the Fermi function kind of broadened out like this. So this is F1. This is the hot side. And the F2, let me draw it, it's very cold. So I'll draw it very sharp like this. Okay. And for this discussion, let's assume the density of states is somewhere here. And what I claim is that this equation basically will tell you, will give you the thermoelectric current. So which way should the thermoelectric current be? Well, it's F1 minus F2. So if I look up here, I see that F2 is essentially 0 because it's cold, whereas here F1 is not quite 0, and so electrons will flow in this direction. So the way the current, you can figure out what the direction of the current is. So remember, this one now has no voltages across it. We're just looking at the short circuit current now. No voltages, just two different temperatures. And the electron will go through this. And so electrons will go this way, which means electrons will come in here, electrons will go out this way. And of course, the direction of the current is the opposite of the direction of the electron flow. So if you actually had to write down the conventional current, the one that you measure, would be the other way here. That's it. So this is how it looks like, usually. Now, that's in an N-type semiconductor. Now, if you take a P-type semiconductor, then the thing is, it's reversed. Why is that? Well, P-type means that instead of something up here, it would kind of go down like this, let's say. And the point is that if you look below mu, actually it is that F that is bigger. This one is smaller. You see, when you were looking up here, this is 0, and that's like, say, 0.2, or some number like that. And so it is going this way. Here, this is 1, whereas this is more like, say, 0.8, so a little less than 1. So when I look at F1 minus F2, I'll find that electrons are going the other way. So this is the interesting point, that is kind of difference between putting a temperature difference and putting a mu difference. You see, when mu's are different, F1 is always bigger than F2 if mu1 is higher than mu2. And so current will always flow in the direction of from higher mu to lower mu. With temperature though, It doesn't have to flow that way. It's like at energies above mu, you'll tend to go this way. At energies below mu, you'll actually go from cold to hot rather than hot to cold. Whereas above mu, it will be hot. Okay. And if you had a constant density of states that did not change, that was more or less the same above mu or below mu, you wouldn't see any net currents. It would be as much above as below, it all cancel out. But if you had an N-type conductor, so you had only density of states on one side, you'll see one direction, P-type another direction.
Graphene, what would happen with graphene?
Graphene? Right, so the density of states would look like this. Okay. So if your mu is somewhere here, if your mu were here, it is perfectly symmetric. It's completely good. If you were here, you'd probably see something because there's more on this side than on this side, so it wouldn't quite cancel. And same reversed on the other side. Right. So the point I wanted to make here is that, so when you're trying to understand this thermoelectric effect and where it comes from, it's that's it. I mean, it just follows from this. There's no new principles involved. It's just this F1 minus F2, nothing. We don't need to discuss this, anything else new. Now, usually when you talk about thermoelectric effect, sometimes people say that, well, the reason this is reversed is because in the case of the valence band, it's actually holes that are moving. But I feel that that's really not a convincing explanation because finally in all solids, what moves is electrons. And holes is at best, it's supposed to be a conceptual convenience, usually. You see, and a physically measured effect should not depend on what I find convenient or what you find convenient. You see, this is a physical effect. You see, and the point I'm trying to make is that the reason it flows in one direction is just this F1 minus F2. This is it really. See? Oh, so but one point I should make is that if you looked at the Hall effect, because one of the things in this discussion I've tried to do is we have said that all that matters is really density of states. We don't have to distinguish between conduction band and valence band necessarily, right? Because usually people say, well, those are two very different things. You treat electrons separately, holes separately, right? But what I'm saying is not really. You can just treat the entire density of states altogether. But let me just qualify that with a little bit, since right before this we talked about the Hall effect. Because usually the way you tell the difference between N and P-type conductors, there's these two standard ways of doing it. One is this Hall effect. And the other is what we just discussed, this thermoelectric effect. These are the two standard ways of telling the difference between N and P. Because just from conductivity, you can't tell usually which is which. Because you just measure conductivity, don't know which is. Now, thermoelectric effect, all I'm saying is it is really all from F1 minus F2. That's it. But for Hall effect, though, there is actually a real difference. It goes like this. But if you look at the density of states, when you look at, say, something here, so this is E, this is like an N-type material, and say this is like a P-type material. And what you're drawing here is a EP relation, and here the E sort of looks like EC plus P square over 2M. Now, when you're describing a EK relation in a valence band, though, it looks more like E equals EV minus P square over 2M. It is going downwards. So in the valence band, when you write a EK relation, you write something like this. And the difference between N-type and P-type comes about because when it looks like this and you put a magnetic field, let's say an electron going this way curves upwards. In a material like this, an electron going this way will actually curve downwards. So that it's not a F1 minus F2 issue, it's a different thing. And that is again only because of this plus and this minus sign here. Because as I mentioned before, the way you think about it is this dP dt is equal to Q V cross B. And I don't quite want to go through the algebra, but one of the things you know is that this causes an electron to go around in circles. You have probably seen this. It's called the cyclotron frequency. And the cyclotron frequency is given by this QB over M. And of course, if in general, when you're interpreting this, this M is like the ratio of momentum to velocity. That's the thing. And so, for example, as I mentioned in graphene, the mass actually increases with energy. And that's again experimentally observed that when you're doing this in graphene, as you have higher and higher carrier densities, the cyclotron frequency actually changes. Whereas usually in ordinary materials, this is fixed. But actually, it's very carrier density dependent in graphene because that mass is energy dependent. As you go up, the cyclotron frequency gets smaller. Actually, okay? Now, in this context, though, the important point is that if you think of this M as this ratio of momentum to velocity, and remember again, velocity is like dE dP, you'll notice that with this minus sign, it is almost as if the mass is negative. See? Because when you look at velocity, you see, as you increase P, the velocity is actually, because the energy is going downwards, it is the sign is opposite. That's the point. And so, there is a difference between this kind of a band and this kind of a band, so that one type wants electrons to curve downwards and the other goes upwards, and which is why the Hall effect is different. Right? But when you talk about the thermoelectric effect, which is what we are discussing, there is no real difference between the two bands anyway. And one interesting point, as a result, I feel is kind of related to this is, when you look at amorphous semiconductors, I made this point that a lot of things we are talking about in terms of density of states is kind of applicable even if you don't have a EK relation. Even if you are talking about anything small where you don't really have an EK relation or an amorphous material. When you go to amorphous semiconductors, they still measure a thermoelectric effect that is quite well understood. There are N-type amorphous materials, P-type amorphous materials. But often, when you do the Hall effect measurement, you get something that doesn't agree with thermoelectric measurements at all. An N-type material shows a Hall effect that has the wrong sign. Very hard to understand what happened. Hundreds of papers trying to understand Hall effect in amorphous materials. Why? Because there is no EK relation. There is no simple picture like this, etc. Okay? Anyway, so that's an aside. What I really want to talk about, what I want to get back to is this thermoelectric effect. And the point I wanted to make is that this thermoelectric effect is really just a consequence of this. And a few years back, I remember we had actually proposed that, there was a lot of controversy in this field of molecular electronics about whether these molecules were conducting through the valence band or through the conduction band. In the way, there's like the conduction is like below your Fermi energy or above your Fermi energy. And what we had proposed is a good way to tell the difference would be to measure the thermoelectric effect. And one question that came up, well, it's a molecule, can you really have do you really have any thermo power? And the point is, because of this, you can see it really doesn't matter where this density of states comes from. And I think it's been about 2 or 3 years now that a group at Berkeley, they performed a series of experiments, actually measuring this thermoelectric effect in molecules. It's a very difficult experiments actually, and they show quite understandable results. What these are. Yes, please.
The rotation should be in the same direction, right? Because the charge sign and change for holes is positive and for vectors is negative.
Yeah. You shouldn't bring in both of those, right? Yeah. So what I'm saying is, the way people usually explain it is by saying that the reason it has reversed is because the sign of Q has reversed. And what I'm saying is that no, what really moves in an inside a solid is always a negative charge. What really moves is always minus Q. And the reason there is a difference is because the M is different. So the thing is that electron with a negative M you could conceptually convert and think as a whole with a positive m. But you shouldn't do both. I mean, don't make it a whole with a negative m. Right? That's the point. Right?
Question, what you're really saying, though, is it's that gradient of that curve that's different between the M and P, and that's where the negative comes from.
Right, that's it.
Not the second derivative.
If you, right, since the velocity is the dE dP. Right, right. Okay, so now you can easily get an expression for the thermoelectric coefficients, for example. So you could say, that from that expression, we could go to a linearized thing where you could say I is equal to G times V1 minus V2. This is what we did before. If you remember, we said, let's use a Taylor series expansion on this F1 minus F2 and thereby write current as just the difference between the voltages. And the point is you could do something similar and write it as some coefficient times T1 minus T2. Now the way we got the G, if you remember, was, write it here. What we had done then was, say, okay, we'll write 1 over Q integral dE. And then for F1 minus F2, I said, let's write it as del F del mu. And then del F del mu gets multiplied by mu1 minus mu2. And then we said that del F del mu was like minus del F del E. That was the way we got a conductance thing. Well, we could do something similar and get the temperature coefficient also. That is, you could say, well, just as you have this, you'd have something like this. Del F del T times T1 minus T2. That's it. Right? And the thing is, here it was relatively easy to turn this into minus del F del E. Here also you can do that, but it takes a little more thinking. Yeah, here this is very easy because when you look at the Fermi function, you find that it goes in as E minus mu. So it's quite clear that if you take the derivative with respect to mu or E, just a minus sign between them. That's it. But now what we are trying to do is take the derivative with respect to T. Right? That's it. So way I could do it is you could say, well, del F del E is like dF dx, I mean dF dx times, derivative of x with respect to E, which would be 1 over kt. Whereas when I do del F del T, it would be like dF dx, and then the derivative of x with respect to T, which is like E minus mu over kt square, with a minus sign probably. Yeah, with a minus sign. So between them, what I can see is that del F del T is equal to minus del F del E times E minus mu over T. Okay. So this is the algebra. So what I need is the derivative of this function with respect to temperature. And what I'm trying to do is relate it to the derivative of this function with respect to E. Since that we have seen before, it appears in the conductance expression anyway. And what I'm trying,
do you take the partial derivative or do you take the full derivative with respect to T? Because the calculation could be dependent on temperature itself.
Right. So in this thing though, when you're calculating it, it's like you're holding the mu constant. Right. So, so that in my thinking, it's like when I write del F del E, it means I'm changing E, but everything else is fixed. And when I say del F del T, it means I'm changing T, but everything else is fixed. So the way it works is if I change E, X changes by a certain amount, and that's why the F changes. And if I change T, again X changes, and then the F changes. And that's why they are kind of related. Because finally, it is all about how F changes with X. And then the question is, a little change in E, how much does it change X? Or a little change in T, how much does it change X? And that's what this part is. And, and yeah, this part is of course fixed, so that's how you. And so just as this del F del mu then became just minus del F del E, which is what we had done before, this one then becomes minus del F del E. But then there is this E minus mu over T in front of it. So the conductance here is like this first one, like we had done before. So this would look like integral dE minus del F del E, and then the conductance. Whereas this one will look like integral dE minus del F del E, E minus mu over T. That's it. So you have this extra factor in there. And this, of course, includes this physics that I discussed, that this coefficient changes sign depending on whether E is greater than mu or less than mu. You know, that physics that I was trying to describe to you earlier, that's all in this math right here, captures it immediately. And so you can see, if you had a, I guess the G also should be there, of course. So if you had a material whose density of states, which is reflected in this function, is all for positive E minus mu, you'll have a positive coefficient. If it's all for negative, you'll have a negative coefficient.
So when you do this Taylor series expansion, so it has to be done around the temperature T1 or T2, right? So when you're writing this coefficient T over there, you T1 or T2.
Right. So whenever you're doing this Taylor series expansion, it is around the equilibrium point. Right? So, and the understanding is that the T1, T2 difference is small enough that it shouldn't matter which one you use. But same with the mu1 and mu2. You could ask the same question, right? To some extent. Right. So the whole, so when you write a T here, I guess, yeah, it could be either T1 or T2. And point is, it shouldn't make a difference because we are talking of small differences such that that doesn't matter.
So when you use these thermoelectric devices, so the normal temperature difference is like about 200 Kelvin or something like that. So is that expansion still valid for that temperature then? Because we're doing Taylor series expansion for small T's, right? So is that expansion still valid there?
Yeah, I guess what is it would depend a lot on the specifics of this function, I think. That if you had a material with a very sharp spike, then something may be valid, otherwise it may, whereas if it is more uniform, it may be valid in a different condition. So that I think needs a more careful consideration. And my thing is that in doubt, you should always just go back to this. This is the one to use really, right? And, but when people evaluate thermoelectric coefficients, that is the expression that they usually use. And actually with conductance also one can ask that when does the Taylor series expansion work in a way. That is, in the sense that, yeah, because your question, you know, you say you have this current versus voltage and you have say something like this, and we are trying to calculate that dIdV. Okay. Now, you might say that, well, you know, we use the Taylor series expansion, and that only applies if the voltage you apply is less than 25 millivolts, right? Because much less than 25 millivolts. Why? Because in doing this expansion, I assume that mu1 minus mu2, you know, it was a very small fraction of kT. That's what allows you to do the Taylor series expansion, because this is in the denominator, so the change in x should be small. So basically it's the change in x that should be small. Now most resistors, of course, usually are linear far beyond 25 millivolts. Why is that? And now that has to do with the subtleties of, you know, earlier I said that when you have a real device, you could, how do you justify using the elastic scatterer model? It would be sort of like you have to think of the real thing as lots of little things in series, where each little thing is the length of an inelastic scattering length, let's say. And the point is, so if in an electrical resistor, you are trying to figure out whether something would be linear or not, whether your Taylor series expansion works or not, I would say that you shouldn't drop more than 25 millivolts across that one little thing. If you're thinking of a very big resistor, then you could easily put 1 volt across the whole thing. You buy a resistor from Radio Shack, you could put 1 volt across it, it's still, 1 kilo ohm or whatever you bought. It's perfectly linear. And then you say, well, how could this be working? After all, it's 25 millivolts. You're putting 1 volt, this theory doesn't hold. But the point is, the way you justify applying it to something that big is by saying that there's really lots of little things and I'm doing a theory on one of those little things. And then you say that, okay, as long as you don't drop more than 25 millivolts over one inelastic length, you are okay. And so I think it's the same with the temperature. The point you raise, I think, is right, that there's an enormous temperature difference, but as long as you don't drop too much across the inelastic length, you're probably okay. That's how you justify it. Anyway, so this then leads to these coefficients that I just discussed. So that kind of just, that slide sort of summarizes what I just said, that you could take that, start from that same expression, linearize it, you'd have something depending on voltage, something depending on temperature, and the first is just the conductance we have been talking about, but then the other coefficient, the GS, that is what will have this E minus mu over QT in it. And that's the standard expression for evaluating that quantity actually. And usually in thermoelectrics, the measured thing is this Seebeck coefficient. And that is, like if you leave it open circuited, what voltage do you get? That is, what you do is you leave this open circuited, so the current is 0. And then you say that, well, for a given temperature difference, how much voltage difference do I get? And that is actually the ratio of this and this. So these coefficients, Seebeck coefficient, that will be sort of like the ratio of this voltage to the temperature, and that would come out as minus GS over G under open circuit conditions. So that's what is usually measured. Okay. Yes. Right. Into smaller.
But then at each small devices you have different intermediate temperature T. So you have to expand at different temperature and then add it up, right? So won't that give you a significant difference in your...
Right. So that is why, so if you had a long series combination of lots of things, so you're putting, say this is 0 and this end is 1 volt, and you're breaking it up little by little. And in one of these sections, let's say you have put 0.01 volt, because you had hundreds of these. So the point I'm making is that when you calculate you are trying to find the conductivity of this bulk material. So what you'll do is you'll assume this much voltage and find what current flows, and you'll take the ratio and extract a conductivity. And that would be representative of this whole big sample. But right. On the other hand, if you said that, well, I put 1 volt, how can it be linear? Then I'm saying that's not quite right. It is this quantity that needs to be more comparable to KT. I mean, much less than KT.
When you have temperature difference, like you have the coefficient like E minus mu over KT square coming, right?
Right, but that T is supposed to be again, if you're using a linear response theory, it is supposed to be a fixed temperature. Right, that is true. So in a big sample, if it is varying, then you have to be careful at one end from the other, because just the average temperature is different. Get your point. Yeah, I see. Yeah, you're right. Okay. So now what I wanted to talk about next is there's a related effect from the Seebeck effect. That is, this is the thermoelectric effect. Here it is, you have a temperature difference, it drives a current. Now there is a related effect and these two are connected. And ordinarily it's hard to see why the two are connected exactly. And this is the other thing I'm saying, you should see it very clearly just from our discussion. And that is that if you have a material that shows a Seebeck effect, so let's say you have something like this, and you put a temperature difference and so a current flows, and we see a Seebeck effect. You will also see something called the Peltier effect. And that is that if instead of a temperature difference, if you had kept the same temperature and just had applied a voltage across it and run a current through this, you would actually cool one of the contacts, cool this contact, and you'd heat up this one. So you'd actually cool, and this is of course the basis of the Peltier effect, which is actually used to make practical cooling devices also. And the two are related in the sense that any material which has a good Seebeck coefficient also has a good Peltier coefficient. So, right, although these two sound like totally different things, and it's not even immediately clear why one had to go with the other. Right? And what I want to explain is in this picture how you would understand that. So the argument goes something like this, that again, for the Peltier effect, let's say we don't have hot and cold, it's all the same temperature, but there's a voltage difference. So that you actually, let's say you're sending electrons in here. Now the point is, that this is the elastic resistor model, and so the electron is going at this energy, but then once it comes out here, of course, we discussed that all the dissipation appears in the contacts. It gets rid of this energy into the contacts, and then when it gets out of the contact, the electron is roughly around μ2 down here. So it goes through here and it heats it up. But look at what happens here. It had to go up in the first place because what comes in from the contact is here and it actually had to go up in order to get through. So, right now we are thinking of same temperature, but there is a difference in the μ1 and μ2, let's say. So this is μ2. So the important point is that if you had a material that shows you Seebeck coefficient, so Seebeck effect, so that the density of states is above this mu up here, then whenever a current flows, you'd actually be cooling one contact and heating the other one. In the past I said that with elastic resistors, what wasn't clear was that this I squared R loss, everyone knows there has to be a Joule heating. Where does it happen? Well, I said, it happens in the contacts. And the point I'm now trying to make is that with these N-type conductors, when you look at it, it is not all heating. It's like one is getting cooled, the other is getting heated. But then it is getting heated more than it's getting cooled. Why? Because, of course, in order for electrons to be flowing this way, since the temperature is the same, μ1 must be above μ2. So, here you'd be cooling, picking up that much energy from this contact, but then you'll be dumping that much here. And what is the extra that you're dumping is like μ1 minus μ2. That's the Joule heating. Overall, of course, you're heating it more than you're cooling. And this minus that is basically the Joule heat. Because every time an electron goes through from here to here, basically what happened was an electron came in at μ1, left at μ2. And so it dissipated an amount of energy that is μ1 minus μ2, which is QV. So every time an electron goes through, it dissipates overall that much energy. Why? Because it comes in here and goes out there and it loses this extra energy, QV. And so if electrons are going through at a certain rate, you can show that the current would, the power would be V times I. Every electron that goes through dissipates that much. You see? And how many electrons go through? It's sort of like I divided by Q. That's the number of electrons going through per second. That's the current. If you divide it by the charge on an electron, tells you how many go through per second. And every time one goes through, it dissipates that much. So what is the energy dissipated per second? V times I. I mean, that's the Joule heating overall, no question. But if you look carefully, what you find is it's not heating everywhere. It's like this end is getting cooled and that end is getting heated. If you look carefully. Now, of course, you wouldn't have this. You'd have just the reverse if it was a p-type conductor. If all your density of states was down here, then you'd kind of first be going down and then be going up. It would have reversed. And of course, if you have density of states everywhere, more or less uniform, then you'd have none of it. All of it just cancels out. There'll be some going above, some going below, etc. But the point I'm trying to make is when you look at it this way, you can kind of see that anything that gave you a Seebeck effect would also give you a corresponding Peltier style effect. You see? It would have this cooling and heating in it, the two ends.
Why the energy supply from the left-hand side should be U1? And the same question, why the energy would dissipate to U2 with the left-hand side?
Good point. Right. So, in the usual situation, the argument was that if this energy is E and this is mu1, so usually we have been drawing the picture like this. And the argument is an electron goes through from here, comes out here. No energy is dissipated. Where is it dissipated? Well, eventually it has to lose this energy and come to the Fermi energy. And that is because I'm assuming this contact has just a constant density of states. So left to itself with enough inelastic processes, all the current will tend to be right around here. You know, according to this del F del E function, it will, that if there is, once it has come back to equilibrium the way it wants to, it won't have all these hot electrons up here, because when you look at the for occupation, once the electron comes out here, you know, this contact really likes to have a Fermi function. And an electron up here looks like an anomaly. I mean, it looks like a big spike at an energy that shouldn't be there. And so all inelastic processes will quickly lower it down. That's what it does. And at this end, same story. It's like it wants to be a Fermi function, an electron left, so there's a kind of spike downwards there. And that's an anomaly and gets filled up quickly from the electrons in here. And whatever comes in here is somewhere here. And overall, what happens is an electron comes in at mu1, leaves at mu2, and thereby gets rid of this energy QV. And that's why the heating is V times I overall. That's the Joule heating. We know that a battery with a voltage V delivering current I, that's the heating. Okay? But in between, you'd say this. So this is how I explain the normal resistor, the elastic resistor, whereas the heating is. And what we are now saying is that in a thermoelectric, it's a little bit like the mu1 is here and the mu2 is here, let's say. And there is a current, but then it is going through this energy. And the only reason you have a current there is because, of course, there's a long tail of the Fermi function. So there are electrons here that are going through. That's how it is going. And now, you see, you first have to cool it before you can heat it. That's the issue. Okay? This was the argument. And if you wanted to write down the heat current, you could almost write it down in a way, in a similar way. That is, you know, what we had here is this I. If I wanted to write the heat current, IQ, it would be so this is what we wrote down here is the current, the electrical current, and the point is every time an electron goes from here to there, the amount of charge transferred is Q, but the heat that is taken out of here is E minus mu1. So the heat current is like E minus mu, and the charge is like Q. So we had an expression for I. If I wanted the rate at which electrons go through, then I should have divided by a Q. That would give me the rate at which electrons go through. And then every time an electron goes through, it removes that much heat. So what I should do is put a E minus mu1 over Q here, if I'm writing the heat current at contact 1. If I'm writing the heat current at contact 2, I would write just the opposite probably. So it's probably between 2 minus U over Q. I think the reason this reverse is just a direction of heat flow, how you define it. I think I reversed it because the way this is chosen, electrons are going out from here, whereas here it is kind of coming in, the way the reference is done. But the point is that when you try to calculate heat current, it almost follows easily from whatever we have discussed before. The main point to note is every time an electron goes through, it transfers a charge Q, but it also transfers an amount of energy, which is E minus mu. And of course, if you're doing linear response, then usually you don't distinguish between mu1 and mu2. You just say that the heat current is E minus mu. That's it. You don't really distinguish between those two. Because there is, of course, a difference between them. Difference between in the sense that the amount of cooling and the amount of heating, the difference is, of course, the joule heating from the battery. But you say that, well, the joule heating is proportional to the current squared. And so for linear response, you can kind of ignore it. And so you just set IQ1 equals IQ2 for the linear response formulas. Yeah.
So for a very linear system, so current flows around the Fermi level. So for that, the heat current is 0.
If the density of states above and below are almost the same, that is true. Which is why probably semiconductors usually make better materials for all this, right? Than metals. Metals also have some Seebeck coefficient, some Peltier coefficient. But commercial devices are usually P-type materials and N-type materials in series.
Because if it's very degenerate, then df dx will be like delta function. So if you replace E by EF or mu, so it is 0.
Right. So finally, there has to be in order to get a non-zero coefficient, there has to be an asymmetry between E less than mu and E greater than mu. Otherwise, as long as it's all symmetric, you won't get any Seebeck or Peltier, any of that. Yes, please.
Is there also a way to define heat current within the device? Let's say in cases where you have non-equilibrium and well, it's maybe hard to define a mu in the device.
Right. Usually, this is why I say that this elastic resistor, this concept, it helps say all those things a little more clearly, because usually when you think of a long device, it is harder to understand what mu means and all that. Whereas here what we are saying is, think of this channel connected to two contacts, and the contacts are big things, so mu's are well-defined things. Right? And so the thing is, you take this electron at this energy, but then the contact, when electrons come in, it comes in at mu. So they kind of have to absorb all this energy from this contact in order to rise up in the long run. And that's why it gets cold. That's the view. Okay? So this is why I said this elastic resistor, because it separates out these two things, it helps clarify a lot of points. And the justification to some extent is that, you see, after all this, the expressions we are getting is exactly the standard thermoelectric coefficient. So in that sense, I'm not telling you anything new. I mean, these are all things you could find in textbooks. It's just that they wouldn't come out quite this easily. That's the point, right? You see? Usually, you'd have to go to Boltzmann equation, etc. And of course, our whole thing is consistent and based on Boltzmann equation. It's just this whole thing of the elastic resistor helps you see a lot of things quickly. That's what. So that's this heat current. So that's what I've written up there, that if you're writing the heat current IQ, it would be exactly what we had before, but now you have added the E minus mu over Q in there. And this one also, again, you could now do a Taylor series expansion, something voltage and another one temperature, and then you'd get a GP and a GK. And what you can see is that, you see, in the last slide, we had taken the, so I had written I equals G V1 minus V2 plus GS T1 minus T2. And now with IQ, we can do something similar. Get a GP V1 minus V2 plus GQ T1 minus T2. You could take this current, expand it the same way, and you'll get all those coefficients. And one interesting thing you'll notice is that this GP and the GS are related. It is almost basically the same coefficient, and that just comes out of doing the Taylor series and all. You get almost the same coefficient, and one is related to the Peltier effect, other is related to the Seebeck effect, which kind of tells you why they always go together. You see, they're basically the same expression. Any material that has a good Seebeck coefficient will also tend to have a good Peltier coefficient, much for the same reason. And again, none of this is not that anything that's not known. In the literature and thermodynamics, this is all consistent with exactly what you'll see there.
That's called the on-Saga relation.
That's the on-Saga relation, yes. Actually, this relation between the Peltier and the Seebeck, that's called this Kelvin relation. But the fact that these coefficients are similar, that's a special case of this general on-Saga relations. On-Saga relations, which says that the flux due to a particular force and the corresponding, this flux due to this corresponding force, they would have to be related, right? That's the on-Saga relation, G12 and G21 in a general sense. So it will be consistent with that, yes. It's just that usually on-Saga relations and all will take a lot more work. It's a lot more subtle to understand and derive. You know, this actually took, many years, lots of discussion to get there. Whereas here all I'm saying is it follows pretty easily for the elastic resistor. That's all. Yes. Okay. Now, as one last example of this viewpoint, what I wanted to talk about next is so far we have always been talking about electron flow. Right? And what I wanted to show is, just with a relatively simple extension, you could talk about phonon flow as well. And this is something I believe Professor Fisher will be talking more at length tomorrow about. His talk is about Landauer approach to phonon flow, in a way. So we'll talk more about this. But while we are on this subject, I wanted to show how you could get that pretty easily, really quickly, actually. So, current, I think the expression we had was integral dE, then we had this G of E, F1 minus F2. G of E was like Q squared over H m lambda over lambda plus L. So this is what we had called this conductance function. And I guess you could cancel out one of the Q's. Okay. But we had written dE, conductance function, and conductance function we had a bunch of different expressions. One of them was this one, and I think in this context this is most useful, which is why I'm writing it. So now the point is, supposing we want to write down what is the heat current due to the flow of phonons. And the thing is that whatever discussion we had about electrons with this elastic resistor, you could have exactly the same discussion about the flow of phonons. Only thing now is that these two contacts, you don't talk about the Fermi function, but you talk about the Bose function. N1 and N2, which tell you how phonons are distributed in energy inside this contact. The electrons have this exclusion principle, so at equilibrium they're distributed according to this Fermi function. And the Bose function looks a little different. So let me just write that. And H of R omega So kind of similar with this is plus, that's minus, of course, that makes the function look very different.
What's the driving force for
temperature? Temperature. So just as here, the driving force was the difference between the two F's, and that difference usually comes from mu, but could come from T. In the case of phonons, we don't quite have a mu, so the only driving force is the T.
Is it kind of density difference or diffusion?
Yeah, though this is the point, though in general, as a general principle, I say that what drives flow is not so much the density difference as this chemical, electrochemical potential difference. That's the point I often try that. Sometimes I ask this question, that if you had a material which had a very high density of states here and a very low density of states here, then when they come to equilibrium, the point is the mu will be the same across. And so there will be lots of electrons here, very few electrons there. It's not like the number of electrons is getting equalized. And it's the same concept that you learned early on, that what drives heat flow is not how much heat this has and how much heat that has. It's a question of temperature. Right? So it's a similar issue here. So what drives it is always this temperature difference. And that is why what should appear here should always be F1 minus F2 or N1 minus N2 in this case. But I've got two reservoirs with two different Bose functions coming from two different temperatures, and that's what it is. That's it. And when I'm trying to write this IQ, then instead of dE, I'd put a dH bar omega, of course. Okay. And the thing is, here we were talking about the rate at which charge flows. Of course, if I take this Q and divide it here, it will tell me the rate at which electrons are crossing over per second. And so, and then I can multiply it by h bar omega to get the rate at which energy is flowing. So my point is, the correct expression here should look something like, there will be h bar omega, and then this m lambda over lambda plus L. That's just, only thing is, here this was all electronic quantities. Now I should be looking at phononic quantities. But otherwise, we are more or less done. That's it. Yeah.
So the omega is the frequency?
Omega is the frequency of the phonon, frequency of the phonon. Right, right. So going from here to here, then all that I did was, there was a, if you remember, so let me put it this way. So the overall expression was that I started with was something like this, and all I did was took the Q out, replaced it with h bar omega. Because every time a phonon flows, it carries that much energy, just as every time an electron flows, it carries that much charge. So that's all I did. I might have said it a little more complicated, but this is all I did really. And then the F1 minus F2 replaced with N1 minus N2.
So lambda here is the
phonon mean free path.
scattering with electron flow, like every scattering with.
However, phonons are getting scattered, right? And often those mean free paths depend on boundary scattering, all kinds of things, right? So those things you'd have to understand a lot about the phonon system to know what to use there and so on. Right? Now this one then, again you could do this linearization. So you could try to get an expression for the thermal conductivity. So G. So you could try to write it that way, and then you'd have a thermal conductivity of this thing. So in order to do that, of course, you need to, again, do the same Taylor series expansion. So it becomes T1 minus T2, and then del N del T. The same thing again. Now in this case, you'll notice, when I take del N del T, I suppose what I should do is like before, dN dx, and then how x changes with t, which would be like minus h bar omega over kt square. dN dx, of course, is like e to the power x minus 1 whole squared, then e to the power x, I think, right? Yeah. I think that's about right. So if I put this in here, then, so for del n del t, what I am getting is, I guess this is dn dx, but then of course this whole thing is there. The minus is gone because, so I think you should get and note that the x of course is h bar omega over kt. So I think this is the expression I have on the this. Basically what you get is sort of summarized up there, that so you'll see this is an integral over dh bar omega with little renaming of variables. You could put a divided by kt there, so it would become like dx and multiply by kt here, and here make this kt square, put a k square there and put the k square there. Could move it around a little bit, and that's how you'd get that second expression. That way it's like k square t over h in front, and then there's the integral dx m lambda over L plus lambda. And then you have this x square e to the power x over e to the power x minus. This is of course a different function from the df de that we have been using all along, because now we are talking phonons. When you do this, you get that function. Interestingly though, that function doesn't look too different from df de. Looks almost the same. That's what I've tried to plot here, that if you take that x square e to the power x over e to the power x minus 1 square, you get that blue curve. Whereas when you take df de and actually multiply by 4, you get that red curve. So it's kind of similar, but not exactly the same curve, of course. You don't expect it to be the same curve, actually. Right? And in a way, actually, I was never sure when I first started thinking about it, how anyone would get this whole theory of thermal conductivity from this approach, because the Bose function, of course, I knew that at x equals 0, it blows up. This e to the power x minus 1, it kind of blows up. And I didn't quite see how you'd get a sensible thing out of this. It seems like something else needed. But when you calculate this, the thing is, you pick up one h bar omega from this energy, and then from this derivative, this another one, so that finally the function you get has this x square in it. X square e to the power x over e to the power x minus 1 square. And that one actually, as x goes to 0, doesn't blow up. Because what you can show is the denominator for small x is like x squared, just cancels out. So it's a perfectly well-behaved function. There's no problems at all, really, as far as this is concerned.
One small thing. When you write the conductance equation, we have the term q square by h. In this thing, we are having a k squared t by h. Can we think of this term as almost like a
quantum of thermal conductance, essentially, almost, right? As far as phonons goes, it is kind of like that, I'd say. Yeah.
So I have this difficulty with Bose function. How can it be a distribution if it blows up? It has to, the overall integral is to converge somehow, right? Because Fermi function is a number between 0 and 1. It's a probability, you can understand it. But here it blows up at x equals 0. It even takes minus values if x goes to, if x is 0, it goes 1
x goes 0, if x goes to 0, this blows up, and this is all related to that whole thing about the Bose condensation and things of that sort, right? So the Bose function is very different with different physics in it, and of course the Fermi function, it applies to electrons with exclusion principle, so that you can have no more than one electron in something, right? Which is where the Fermi function goes from 1 to 0. So you either have it's either 1 or 0, and in between means that sometimes it's full, sometimes it's empty. That's how it's. Whereas with photons or phonons, they don't have that exclusion principle, and millions of them can be in the same state. Right? A laser, of course, puts lots of them into one particular omega, etc. But at equilibrium, this is the distribution that people believe.
Yeah, usually have a 0 point energy at the best that kind of not very good.
Where you are, so you could argue that for a given h bar omega, there would be the half h bar omega energy that goes with it. That was the argument. Okay. So, yeah, so when you look at it this way, then it looks very similar to the conductance formulas the point I was making. That instead of q square over h, it's this k square t over h. Right? And then there is this internal thing with the m lambda over L plus lambda.
I have a question. So the Gauss function, what does n actually mean? Like, so we have n h bars, what does n actually mean?
So the average number of phonons or photons in a particular frequency mode, right? So one of the first times it was used probably was, suppose if you are counting the number of the black body radiation, for example, from something, you'd see that. So there are various places you'd see all of that, right? Yeah, actually this Bose and Fermi, both of those follow from a much more general principle of statistical mechanics, which is that the general principle of statistical mechanics is that if you have a whole bunch of states, then the occupation of these states is proportional to e to the power minus e over kt, the energies involved. Now, with Fermi, with exclusion principle, things that obey exclusion principle, you say that there's only two states. There's a 0 or 1. And so you say that the probability of being here, let's say is 1. Probability of being here is e to the power minus e over kt. And of course, overall probabilities must add up to 1. So let us say we divide it by z. I mean, the z is some constant, which we figure out so that the sum is 1. And from that you can get the Fermi function. I'm not going into it, but it's standard thing. Now, if you apply the same principle to something with lots of states like this, 0, 1, 2, and no upper limit, and add up all of these, then you'd get the Bose function. So in that sense, both are kind of derived from one general principle, you could think of it. The general principle being, so what is different is with electrons, anytime you have a state, you can either occupy it or not occupy it. That's your option. Nothing else. You can't put 2 electrons in there. With bosons, it's like once you have a state, you can occupy it, you can put 2 in there, you can put 3 in there, you can have 4 in there, all these possibilities. And then you find the average.
So I guess under high temperature, x is small, and n is about kT over h bar omega. I think they call that equipartition or something.
Equipartition theorem, that's true.
You get some simple answer then? Can you get some simple expression for G at room temperature with that kind of argument?
Oh, for the conductance itself? Oh, I see. Because a lot of the h bar omegas involved are probably comparable or less than kT. And that might, because usually when you are calculating the energy in a particular mode, this is the number of phonons in a particular mode. If you want the energy, then you have to multiply by h bar omega. So what happens is, if you want the energy in a particular mode, you'd write h bar omega over e to the power x minus 1, which would be like x divided by e to the power x minus 1 times kT. And this one doesn't blow up either, as it is. See? And so if you actually looked at the energy in a particular mode, that wouldn't blow up. Somehow just this, you have this millions of them with not much energy. Right? But the point you were making was that when x is small, then I guess this becomes 1. And so the energy per mode is kT, which is this equipartition theorem. Right? But when x is large, it cuts off. So when you actually look at the energy per mode, it stays fixed up to a point and then drops off. Okay? That's and the low frequency end is kT, and in the long run it drops off. Okay? Now this k square T over H, that actually has the dimensions of, I think, watts per Kelvin. So I think it comes to about, I forget, 80 picowatts per Kelvin or so, I think. Right, because this has this, you can put in the numbers, I think this is what you'll get. And so just as when we talk about conductance, I made this point about when you look at conductance, it's like Q squared over H, and then there is M lambda over L plus lambda. And so if you wanted conductivity, you would look at Q squared over H, M over A, M lambda over A. So last day I was trying to say that when you are trying to estimate the conductivity, I think we went through an example of how you would estimate the conductivity of, say, copper. And the way you could do it is you could say, well, this is the quantum of conductance, standard thing. The real important point is how many channels do you have per unit area when you're thinking of a big conductor. And then there is the mean free path. So from this point of view, what determines the conductivity of something is that around the Fermi energy, this chemical potential, how many channels do you have per unit area? And then there's also the mean free path. And this is then what I identify as a conductivity. And for phonons also, then we are having a similar expression. You see, it is like K squared T over H. And again, you could ask the same question. What is number of modes per unit area? And then what is the mean free path? Same issues, okay? Now, what determines this number of modes? With electrons, I said that the way you can think about it, which is not immediately obvious when I define modes as D times V, but with some discussion you can see it, is that it's like how many wavelengths fit into a cross section. And the big difference between metals and semiconductors is that metals, the Fermi energy is such that the wavelength is almost the atomic distance. So basically, how many wavelengths can you fit in a cross section? Well, it's almost like asking how many atoms do you have in a cross section, essentially. You see? And whereas in semiconductors, the de Broglie wavelength is more like tens of nanometers. And so the number of modes is a whole lot less. And that's why semiconductors conduct a whole lot less, because mean free paths, if anything, semiconductors have much better mean free paths, really. So it is really the M that cuts it down so much. Now, the thing is with phonons, the number of modes is almost like this electrons in metals. It's almost like you got, if you look at the phonon wavelengths, those are the highest ones are compared, what matters, of course, is, the wavelength of a phonon, of course, changes with energy. And what matters most is, again, average energy, which is of the order of kT. Because the peak of that curve, if you look at how far it spreads out, it's a few kT. And so, if you look at the corresponding wavelengths of phonons, it's again atomic distances. So the point is, when you look at the number of modes involved in thermal conductivity, usually it would come to about this number of atoms. So what I mean by that is, this number here, M over A, that number would be roughly 1 for every, 3 angstroms by 3 angstroms, so 0.3 nanometers by 0.3 nanometers. If it was 1 nanometer by 1 nanometer, you would have put in probably 10 to the, how many per unit area? So you'd have put in about 10 to the 18th per square meter. If it was 1 nanometer by 1 nanometer. With 0.3, you'd probably put 10 to the 19th per square meter. And the mean free paths for phonons, they vary widely. The best thermoelectrics, of course, thermoelectrics are materials where you really want to cut down the thermal conductivity, because you're trying to, because thermal conductivity kind of get in the way there. And those are usually the best ones are those with very low mean free paths. You try to use materials where the phonons have very low mean free paths because of various grain boundaries or other reasons inside. And so then this can be, say, even 1 nanometer. Or it can be much longer, 100 nanometers or so. And so a lot of the difference in thermal conductivity that you see between materials is because of this big difference in lambdas. Not so much because this changes widely. There isn't quite the equivalent of metal semiconductors that I've seen. It is more, they're all basically like metals as far as modes go.
Could you run through that argument once more? Why is the wavelength so short?
Why is that? This is the argument I went through. Oh, By the way, just to complete that, yeah, if you put in this 80 picowatt per Kelvin and go through this, you'll get numbers of, typically like what you see for thermal conductivity of materials. It would be about right. Now, so the argument with that one would be that you're trying to find the wavelength, let's say. And so with phonons, omega is equal to velocity times k. So this is the velocity of sound times k, and the k is like 2 pi over wavelength. And let's put h bar. So, and let's say we are looking for a phonon whose energy is kT, saying that that would be a typical one. So that is then equal to HCS over lambda. So the corresponding mean free, so by the way, this lambda is de Broglie wavelength, nothing to do with the mean free path, totally different thing. Lambda de Broglie is equal to HCS over KT. Now typical sound velocities are kilometers per second, 3 kilometers per second, that's the numbers I have. So when I put those in, this is the kind, I tend to get wavelengths that are in nanometers, or less than a nanometer.
Yeah, they move so much slower than electrons.
Say this again?
They move so much slower than electrons.
Although the CS is, I see. That's what is making the wavelength short is, or yes.
I'm thinking electron wavelength should be different from a phonon. This, a metal's a good conductor too, right, for heat. And so you're saying the wavelengths are the same.
The de Broglie wavelengths.
Phonon wavelength in a metal is the same. Is that what you're saying? And that's,
yeah, wavelength wise they are quite similar, which is why as far as the number of modes go, phonons seem to have much the same number as electrons in metals, as far as the number of channels go, right? Because of the number of wavelengths. That's what I seem to be getting. Right.
So this is why CT is so low. You have electrical conductivity divided by
thermal conductivity.
You have M of electrons divided by M of phonons, and that's always going to be small.
Right. That does look like a problem. That is true, right? From what I have seen. But this needs a lot more thought. I have not given all this careful thought. Yeah.
So this phonon transport is mostly by acoustic.
Mostly acoustic phonon.
Their wavelengths will be very large. If you are not considering zone boundary.
Yeah, though a lot of the zone boundary ones are also involved. Right. So, you draw this omega k picture. So, acoustic phonons, the ones we can hear are probably way down here. But what conducts heat, I think, is a lot of these also.
But from that, if you go to the zone boundary, then your velocity getting less and less.
When you get right here. But around here, this is still comparable to an atomic distance, right? Because if you were here, then the wavelength, I think, would be atomic distance, right? If you're at the zone boundary. But it's getting comparable, is all I was saying. A lot of these, because there's a lot more modes. Density of modes goes up in energy also. But then it gets cut out by that function, the e to the power, the Bose function. But that's why I said KT may be a good number to go with, but it could be less than KT. All that needs careful discussion though. But the thing that is different I notice is that while with electrical conduction there is this orders of magnitude difference between a metal and an insulator, there is no such comparable thing here. Which is why thermal conductivities don't really differ by major orders of magnitude. It is within a relatively short window, a small window really. That's what I've seen so far. Okay, thank you. Yeah, let me stop here. And
nanoHUB.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
So, this morning we talked about this quantum transport, and what I'll be talking about now, though again in a way we'll be going back to the semi-classical picture, because much of what I want to illustrate is how this elastic resistor model you can use to understand all kinds of different physical phenomena. And what I'll be talking about is thermoelectricity and heat flow. And for that, again, one could include quantum effects. It's just that basic things you can understand fairly well without bringing in any quantum effects, really. So we can go back to the semi-classical picture. But before I start on that, let me just say a word about just summarizing what we did in the morning. And that was that, as you know, the basic thing I was trying to express is how in semi-classical picture, just as the Boltzmann equation is the central thing. I mean, it's anything you describe is basic. Boltzmann is what captures all the physics. The point is to understand it and try to use it. And the elastic resistor then is a good way to understand a lot of phenomena. The kind of quantum version in my mind is this NEGF. So in a way, what Boltzmann did, and this was his crowning achievement of this 19th century in a way, is he took Newton's law and he put scattering and all that into it and turned it into Boltzmann equation. You see, Newton's law, which describes mechanics, reversible processes. Into that, he included these irreversible scattering processes, and thereby came up with this equation. And as I said, what he did was so subtle that in his time it was very controversial, and even now you see people writing phys rev letters, papers in phys rev letters about what exactly he did and the meaning of it and the implications of it. Okay. But upon that side of the sample. So as a result, you have almost a very good ballistic conductor, because you see it's very hard to backscatter if that other thing is way out there on the other side, essentially. So something non-trivial happens. That is, usually in a conductor, you expect the density of states to be more or less uniform, spread out all over. But in this high magnetic field regime, actually you have what you call these edge states. And these are things, of course, there have been lots of papers about it and in terms of understanding all this. And as I said, the power of NEGF is how it allows you to calculate a lot of this, even if you don't quite follow what have happened. And so, for example, in the NEGF equations I showed you, there was something I call density of states. There's a matrix there. Just as there's an electron density matrix, there's a density of states. And you could look at its diagonal elements and actually plot out what the density of states is at different points in the sample. So for example, here I've shown a calculation at high magnetic fields. So what is over there is this grayscale plot. This axis is energy. That axis is the width of the conductor. And if you see a white spot, it means there's a lot of states there, high density of states. So what you're seeing is the spatial distribution of the density of states. How was this calculated? Again, with NEGF, you put in H sigma, etc., and using those equations, you calculate it. And you see those white spots in the middle. Those are what are called Landau levels. Actually, at high energies, at high magnetic fields, you have discrete levels at different energies. But the interesting thing is, if you look, there's these white streaks. I don't know if they come out here well. You do not see this very well. Right near the edges, there are these white streaks, which are basically the edge states. Actually, I see that well on my screen, not as well up there though. But right around the edges, there should be these white things. And the way people think about it is that, well, electrons in a magnetic field, they want to turn as you know, in a magnetic field, they want to go around like this. Why? Because the understanding is that dp dt, as you know, when you do semi-classical dynamics, dp dt is equal to force. So it's like Q V cross B. And if your magnetic field is perpendicular, then it tends to turn you. And this you can show that as a result you want to turn, and if you're in the middle, you will tend to go around in circles, and those are the usual Landau levels, etc. But when you're near the edge, you'll tend to do this. Hit that, do this. This is what people call skipping orbits. And that's how people sort of picture where the edge states came from. Whereas ones that are going this way tend to do this. So all the northbound people stick to one side, southbound people stick to the other side, so makes it a perfect ballistic conductor in a way, you see. And net result is if your Fermi energy happens to be there, the actual, this resistance is given by this without any backscattering almost. Whereas usually with ballistic conductors, they are kind of semi-ballistic in the sense that you get Q square over H times M, within a factor of maybe 5% or 10%, because there's always some backscattering. But what made this quantum Hall very special when it was discovered in the early 80s was that the resistance they measured was like quantized to like the 7th place in decimal. It was very accurate. Something you never expect in a solid. Usually to make measurements that accurate, you have to go to vacuum. You see? So that was what was really surprising and unique about it. And I think that was probably the first experiment where this quantum of conductance kind of played an important role. These are fundamental constants which have been known a long time, but this combination was not quite as well recognized in general. Right? So there's one experiment where it actually played an important role. And again, so as I said, if you are trying to learn NEGF and doing, this is a good test problem once you have done the 1D thing, because 2D has more details in it that you have to worry about. Okay. So what I wanted to talk more about then today in this lecture is about the heat flow. That's the second, the topics down here. Right? What we talked about in the morning was what's up there, this thing. And the basic fact, experimental fact is, I guess, let me explain this, is that if you take a piece of semiconductor, then one experiment that is very easy to do, I guess even I have done this, is that if you put down two probes, one hot and one cold, then there's a current that flows, even without any voltage. Right? Or if you don't allow the current to flow, then a voltage would be developed. Right? So this is what the hot point probe experiment. So in this picture, I could say that if this side was hot and this side was cold, then a current would flow in a certain direction. And the thing is, the interesting point is that the direction of that current is different in N-type semiconductors and in P-type semiconductors. Okay? The question is why? And what I claim is that we don't need anything new to understand this. That's all right here. If you just take this, and the way we said it was the Fermi functions in the two contacts are different because you have applied a voltage. We had two different chemical potentials. But supposing we consider the situation when the chemical potential is the same, I have not applied any battery, any voltage across it, just the temperatures are different. Of course, that would make the Fermi functions different, because you see the Fermi function is E minus mu over kT. Usually the reason F1 is different from F2 is because mu1 is different from mu2. But let's say no voltages. All the mu's are the same. But that's fine. The F's are still different. There's a KT1 and a KT2. They're two different things. And that's why you have a current. And what I claim is, that will, just from this point of view, you understand all the basic things of thermoelectricity, the standard stuff. Right? That's what I want to get across. So the picture I had drawn before, you had a density of states here, and you have a mu, and this is mu1, and this is mu2. Yeah. So the point is that just as Boltzmann needed to do something with Newton's law to get all that in, once you replace Newton's law with Schrodinger equation, quantum mechanics, you again have to do something similar. This is just as Newton's law wasn't enough, Schrodinger by itself isn't quite enough. You have to do something else. And NEGF is one way I know, which essentially does that in a consistent way that is comparable to Boltzmann in exactly the same way. And those were the equations of the Boltzmann, of the NEGF formalism. And what it includes, of course, that is different from Boltzmann is that it includes interference effects, essentially. And as I said, if you are trying to learn this, then two good examples to go through are first the one-dimensional example that I mentioned, about various scatterers, see how you get resonances out of the quantum. If you want to include dephasing processes into the NEGF, then you can actually turn the quantum calculation into the classical calculation by destroying the interference. So that's usually a nice example to go through. The other example, I say if you are kind of comfortable with the 1D, then I'd say let's try the 2D. And a good 2D problem is this Hall effect problem. Just a 2D conductor, you can first calculate conductance without any magnetic fields, then see what happens in a magnetic field. And one of the interesting things that actually happens in a magnetic field, which I won't go into, is that at high fields, you see that Hall resistance, you'll see show those very sharp plateaus, very nice plateaus. And that was the first example probably where this quantum of conductance played a very important role, in the sense that Hall resistance actually looks like h over q square times an integer. And one way to understand it in the context of what we are talking about is that what happens at high fields is that the electrons that are going in one direction tend to have their wave functions on this side of the sample, while the electrons that are going in the other direction tend to have their wave function